Hi, in this video I want to talk about the difference between binomial random variables and hypergeometric random variables. In short, if you just came for a quick answer, the difference is that in hypergeometric random variables, the outcomes are not independent, right? So you do sampling without replacement. In the binomial distribution, binomially random variables, the outcomes are independent, and so you have sampling with replacement. Okay, but I'm going to go ahead and do an example of each of those scenarios, and I'm going to talk about also the binomial approximations of hypergeometric and why that makes sense. All right, so first let me go ahead and zoom in and let us look at the criteria for the binomial experiments. All right, so in a binomial experiment, very important, you have a set number of trials. Okay, so in this case we have n trials, and each trial is independent and identical. Okay, next criteria is that there must be two possible outcomes, right? So every trial has two possible outcomes, either a success or a failure. Next, the probability of success is the same for each trial, and our random variable is going to be the count of the number of successes. Okay, so this is the binomial probability distribution or probability mass function. Sometimes you'll see it written as the probability x equals x. Sometimes you'll see it written as f of x. Sometimes you'll see it as b x colon np. All right, they're all the same thing. This is the binomial distribution function or binomial probability mass function. Okay, so let's go ahead and do an example. Okay, so the classic example for the binomial probability distribution function is the flipping of the coin. Okay, well, so let's talk about this flipping of the coin. We're going to flip it 5 times. All right, so since we flipped it 5 times, it's basically there's 5 trials. Okay, so 5 trials, and so that means n equals 5. There are 5 trials. Now, are these trials independent? When I flip it, what happens on one flip has no influence on what happens on the next flip. So yeah, they're independent trials, and they are identical as well because it's the same coin, right? So I should be having identical probability of outcomes each time. Okay, so first criteria of the binomial experiment, it's met. We're going to count the number of heads. Okay, so there are 2 possible outcomes, either a head or a tail, right? And so we are going to count the number of heads. So that meets the criteria of having 2 possible outcomes, and our random variable x is the count of the number of successes, or the count of the number of heads. So let me go ahead and define x as being the count of the number of heads. In this case, a head is going to be what is called a success. All right, so we count the successes. All right, next we're going to find the probability of getting 4 heads and 5 flips. All right, so one thing that we're missing here, we need n, x, and we need p. Remember, what is p? It's the probability of success, and it needs to be the same for each trial, right? And each trial is identical, so it will be the same. So what's the probability of success in this case? What's the probability of getting a head? Probability of success should be the same as probability of getting a head. In this case, it will be 0.5. All right, so because there's 2, they're both equally likely, head and tail, right? All right, so now let's go ahead and write down our probability distribution function. All right, and choose x, p to the x, q to the n minus x. All right, so n, we've determined, is 5. Oops, what am I trying to find the probability of? Let me not get ahead of myself. I'm trying to find the probability that x equals 4. We're trying to find the probability of getting 4 heads and 5 flips. So we're trying to find the probability x equals 4. N is 5, x is 4, p, probability of success, is 0.5. Brought to the power of x is 4. Q, what's q? Q is the probability of failing, okay? So that means probability of getting a tail in this case. Well, what's the probability of getting a tail? It's also 0.5. So in this case, it would also be 0.5. N minus x would be 5 minus 4. All right, so you go ahead and solve that out, and you can find the probability of getting 4 heads out of 5 flips. All right, so that's a very simple example for the binomial distribution. But most important things that you saw here is we defined the number of times that we were going to flip the coin ahead of time. Okay, so we defined the number of trials, that there were 2 possible outcomes, that each trial was independent of the previous trial, and the probability of getting a success for each trial was the same. Every time we flip the coin. Okay, so we use the same coin. All right. Let us move on to the hypergeometric distribution now. Okay, so now in the hypergeometric distribution, we still have n. You still see the same n that you saw in the binomial distribution, except now n is the number of items selected without replacement from a population of capital N items. Okay, so before n was just the number of trials. There was no, big N in the binomial distribution. Now there is a big N for the hypergeometric distribution. All right. Each item can either be a success or failure. Ooh, that's exactly the same as the binomial distribution, where we had 2 possible outcomes. Okay, so that's the main thing that ties binomial and hypergeometric together. X is the count of the number of successes in the n selected items. That's also very similar to the binomial distribution. Okay, so our random variable, it's very similar. Main difference here is this top piece, that there are n items selected without replacement. So these trials are not independent of each other. They depend on each other because we do not have replacement. Okay, and then this is our probability distribution function. Okay, sometimes you'll see this written as an f of x again, or you could see it as an h with all the different x and capital N and K in there. Okay, so let's do an example and we'll talk about how to use this guy. Okay, the most classic example for the hypergeometric distribution is a deck of cards. Okay, so I have a deck of cards here. So this is my population. I'm going to be selecting from this deck without replacement, which tends to be the way we select from decks, right? Like if I'm playing a card game, I'll give you 1, 2, 3, 4, 5. That's your deck, right? That's how we play cards usually. So usually we select from a deck without replacement, right? Unless you're doing some sort of magic trick or something. But like when we're just playing games, usually you hand someone their deck, or you hand someone their cards without replacement from the deck. Okay, so without replacement means I give this to you and I don't put it back before I give you the next one. Okay, so that dependent relationship is what's going to make this an example of a hypergeometric distribution rather than it being a binomial. All right, the fact that I am not putting the card back in the deck before I give you another card. All right, so we have 10 cards that we're going to select from the deck without replacement, okay? And we want to find the probability of selecting 3 kings, okay? So just like in the binomial distribution, we have a success and a failure, right? Either you get a king or you don't get a king, right? So you still have the success or a failure, but the main difference being now that when I select a card, I give you another one, I give you another one, I give you another one. I'm randomly selecting cards from the deck, but I'm not putting in the previous card back into the deck before I give you another one, okay? If I was putting the card back into the deck each time and then giving you another one, then I'd be back to the binomial, right? Because the probability of getting a king each time I pick a card and then put it back, randomly pick a card, then put it back. That, with replacement, that would make this a binomial distribution. But because I'm handing you the cards and not putting them back in the deck, I want to find the probability of getting 3 kings, that's what makes this a hypergeometric distribution. Okay? All right, so this is a hypergeometric distribution. I am selecting little n equals 10 items or 10 cards from without replacement, very important, without a replacement, from a population of 52 cards. Each item is a success or a failure, right? Because either a king or not a king. And X is the count of the number of successes, or the count of the number of kings out of 10 cards. So X equals the count of the number of kings in 10 cards. Okay, so X could either be I get 1 card, I could get 2 cards, I could get 3, I could get one king, 2 kings, 3 kings, actually up to 4 kings, right? But I can't get 10 kings. Why not? There's only 4 kings in the deck, right? So the most X could possibly be is 4 in this case. All right? And actually, the number of kings that are in the deck, that's what we call K. K is the number of successes in the population that are possible, right? So there are 4 kings in the deck, so that's what K is. So K is related to N here. So actually, let me put it next to it. Okay, this is population. This is coming from the population. All right, so X is related to the sample. It's the count of the number of kings in the sample from the 10 cards you get. Okay, so what I want to know what's the probability of X equaling 3. Remember, X could equal 1, 2, 3, or 4, and we want to know what's the probability of getting 3 kings. And we've been given 10 from the deck. All right, so actually first let me go ahead and write down the distribution so that way we can talk about how to use it. So the distribution is K, choose X, and then N minus K, N minus X, N over N, and choose N. All right, so now we just need to plug in what we know, and then we can solve this probability. So if I want to know what's the probability that X equals 3, I would do K, which is 4, choose 3 times N minus K, so 52 minus 4 is 48. N minus X, N, little n, remember, is 10, minus X would be 3, so that's 7. Okay, and then all of that divided by N, which is 52, choose 10. Okay, what's going on here? This is the number of ways you could have chosen the 3 kings that you got from the 4 possible. This is the number of ways you could have chosen 7 cards that are not kings from the remaining cards. And this is the total number of ways, divided by the total number of ways you could have selected 10 cards from your entire population. Okay? All right, so that's the hypergeometric experiment. So next, I want to talk about the hypergeometric approximation to the binomial experiment. Okay, so let's go ahead and zoom in and look at that. Okay, so we can use the binomial distribution to approximate the hypergeometric distribution if the number of objects that are selected without replacement are from a large population. All right, so basically, if your population is so big, then whether or not you put the card back in, it really doesn't really matter because your population is so big. Okay, so it's always easier. The binomial distribution is slightly easier to calculate than the hypergeometric. That's why we like this approximation. Okay, and so we would use this only for large populations. Okay, so what's considered to be a large population? A large population is, a lot of times the rule of thumb is that if the sample size is less than 5% of the population, then that's basically a large enough population. Okay, so let me do an example where we can talk about how to use this approximation. Okay, so now let's do an example where I have 3 decks of cards. So my population is not just 1 deck, not just 52 cards, but 3 decks, 156 cards. Population just got bigger, okay? Now, cue to trying to see whether or not you want to be using the hypergeometric or the binomial distribution's approximation to the hypergeometric is you want to think about, is my population size really big? Okay, so once you think, oh, is my population size really big? This is hypergeometric. Can I use the binomial approximation? That's when you need to actually calculate if your sample size is going to be less than 5% of your population. Okay, so now I have a big population. I have all these cards, 156 cards. Okay, big population. And what I want to do is I want to select 5 cards from this. So I'm only selecting 5, very small number of cards from this big population. And I want to find the probability of selecting 4 kings. So again, there's either a success or there's a failure, getting a king or not getting a king. Now, if it said with replacement, this would be binomial, right? Because if I pick up a card, I see if it's a king or not, and I put it back, right? So that would be with replacement. And since each trial then would be independent, if I put it back, probability of getting a king each time is the same because I'm putting it back, right? That would be a binomial distribution, right? But I'm not putting it back. I'm going to select 5 cards randomly from my deck, and I'm not going to put them back each time. Now, the thing is, the reason why that doesn't really matter that I'm not putting them back, and the reason why I'm able to basically use the binomial distribution despite the fact that I'm not using replacement, is because this population is so big. Whether or not I put it back, it really has a very small influence on the probability of success, right? The probability of getting a king, in this case, since I have such a big deck. Let's see, actually, what is the probability of getting a king? We're going to need to figure that out eventually. So the probability of getting a king, right, the first time I draw it, how many kings are there? There's 3 decks. Each deck has 4 kings. So there are 12 kings out of 156 cards. Now, that's the first time I draw. But the next time I draw, if I don't use replacement, then how many cards are in my denominator? 155 cards, right? And it also depends on whether or not I got a king. That influences what the probability of this one being a king, right? So if this first one was a king, I would only have 11 kings left in the deck. So, you know, there's a dependent relationship here as I pick, right? But the point is that dependent relationship, as the sample size gets larger, that taking 1 off of 156, it's really so minor, it really doesn't have much of an influence on your probability of getting a king, right? So like 12 divided by 156, it's really quite similar to 12 divided by 155, right? And you can imagine as your sample size increases, 12 divided by 1,000, it's really similar to 12 divided by 999. Right? So, you know, with really large sample sizes, we're allowed to just basically forget the fact that we didn't put it back in, okay? So we're basically able to pretend like we used replacement even though we didn't, okay? That's the binomial approximation to the hypergeometric distribution. Okay, so let's talk about how to use it. All right, so even though this is a hypergeometric distribution, we're going to pretend like it's a binomial distribution, basically going to pretend like there was replacement, okay, even though there wasn't. All right, so remember in a binomial distribution, x is going to be count of the number of successes, so count of the number of kings, okay? So P, probability of success, will be the probability of getting a king, which is 12 over 156. The number of trials, n, we have 5 trials. We're selecting 5 cards. Okay, so remember our binomial distribution. N choose x, p to the x, q to the n minus x. Okay, n choose x, so this would be 5. Oh, let me go and write this. Probability, we're trying to find the probability that x equals 4, that we get 4 kings. So 5 choose 4, p is 12 over 156 to the power of 4, and then q, what's q? Remember, q is just probability of not getting a king, basically, probability of failing. So that would just be 1 minus whatever p is. So I'm just going to write it like that. 1 minus 12 over 156. and then you would bring that to the power of n minus x, so that would be 5 minus 4. Okay, and then you would just go ahead and plug that into a calculator, and you would solve and find the probability of getting 4 kinks. Now, if you're interested in knowing how good of an approximation this is, you could always use the hypergeometric distribution. You're just going to get really big numbers when you plug it in. So you could use the hypergeometric distribution, realize that the entire sample, capital N, is 156, that little n is 5, that the x, we're trying to find the probability x is 4, and then k, the number of successes in the population, would be 12. Okay, so you could go ahead and plug this into the hypergeometric distribution and solve this, solve the hypergeometric distribution, and see how similar the answers are, and they should be quite similar.